All right, thank you very much for the introduction, and thank you. I would like to thank the organizers for the invitation. So, my topic rather lies slightly at the borders, let's say, of the general theme of the conference, perhaps. But I think I can convince you that I'm going to show you some interesting stuff that is directly actually relevant to most of the work in some sense. So, actually, I'm not going to go do a rigorous introduction, but first I would like to talk about why phase transitions. Basically, it's the most ubiquitous concept in pretty much all physics. I mean, we have been hearing about a lot about systems that exhibit basically phase transitions. So, and then, many correlated systems actually are associated with phase transitions. If you look at these examples, for instance, in the case of doped cuprates, all these different phases, they are basically, by changing the concentrations of the copper or oxygen or other ingredients here, you can tune the temperature or the pressure, whatever you like, the extrinsic parameter, where the phase transition takes place. Another perhaps very interesting example that has been recently demonstrated is twisted bilayer graphene, where you have, again, basically phase transitions through various quantum matter. So, in one case we are dealing with a very complex system, and in the other case I would say we are dealing with an extreme system where the phase transitions happen at very low temperatures and so on. So, but these are not the only two examples actually that we can find. Actually, if you look at this list, there are many other materials, and this is not by far, it is not a complete list, it's a very limited list. So here I'm going to focus on VO2 and basically, these correlation effects actually lead to the phase transitions that I already mentioned. So I spent quite a lot of time with VO2, so I'll continue my introduction with VO2. In the case of vanadium dioxide, this is a very simple transition metal oxide, which exhibits a phase transition at about the room temperature. And it goes from being an insulator to metal if you increase the temperature, and a structural phase transition is associated with it. This is an interesting transition because, this resistivity changes on the order of 5-6 orders of magnitude, and it is coupled to this optical phase transition as well. So, in our past efforts, actually, we tried to understand this phase transition, and we applied strain using a MEMS device. And if you could play the video, and by changing actually this gap size, you can see that this phase boundary can be controlled, and this allowed us to extract a phase stability diagram of this material and triple point in a solid state system for the first time. And the insulating phase, if you look at it, is not a regular insulator, and we also studied that in the past, and we basically demonstrated that it is not your regular insulator. This is somewhat expected. And obviously, the dream dream here is controlling this phase transition using an electric field. And the problem is basically, people tried it really hard, but the Thomas Fermi screening length is very short. So basically, it's quite difficult to modulate. But I took my shot on this one as well. So we developed a method to mill down VO2 crystal, single crystal, that's very important. And we try to, gate it, but unfortunately it is not a gateable material. So, even if you have a very thick VO2 crystal that is freestanding on an HBN substrate. So, this is very interesting and good, but these major limitations actually somewhat put me away from the studies of VO2. Now, back to the drawing board, we have these systems and we have this table. So I want to figure out ways to obtain simple materials that can exhibit phase transitions through the strong electronic correlations. So if I take a step back and show you the kitchen of this thing, the examples that I showed you on VO2 is about basically by using these nanobeams. And there's a very good reason. If you use epitaxial films or these sputtered polycrystalline films, the interaction between different crystallites actually hinders the mechanisms that you expect to observe, or the phenomena that you expect to observe, I'm sorry, in VO2. And same goes for these epitaxially grown films. Basically in epitaxy, your crystal follows the substrate, and this exerts a strain on the crystal. Thus, it leads to complications and thus irreproducibility in measurements. So this extrinsic effects must be controlled. So we need to have single crystals, pure forms, so that we can study these effects. So the best way to do it, the best way to obtain a crystal, in my line of work at least, is chemical vapor deposition. You put the precursors, you put your substrate, you close the lid, and then you have a working recipe, hopefully, and you obtain high-quality crystals, right? It's easy to implement. It has low running cost, but the recipes are typically very irreproducible. You cannot, even if if you make slight changes in your system, you cannot reproduce your recipes. It's a black box, so you cannot optimize. So how can you synthesize new crystals with such a system? Well, it's not possible. So we had to design something new so that we can fabricate new crystals. Now, the idea is, have an optical window, have your CVD happening here, and then observe the crystal synthesis in real time. Well, we performed some thermal simulations and some preliminary work, and also there has been some trials before what we introduced. And then we created this complicated looking setup. So this is now our CVD furnace, this aluminum box here. And it is basically placed under an optical microscope, and you have your crucibles inside, and you can see it glowing actually at 950 degrees Celsius, and you can see the substrate. So we can observe the CVD process in real time while controlling all the parameters, the gas flows, and so on. So this gives us a real-time feedback, perhaps. So if you could play this video as well. This is an early example. What you're looking at is taken at 790 degrees Celsius, 4x, and this is the scale bar. These crystals are tungsten diselenite monolayers, and actually you can see different growth modalities taking place in the same growth. So by doing that, we can, I call this the Ferrari of CVD furnaces, because I can put the brake, slam on the brake, and then I can freeze the growth, then characterize what's happening. And this, I'm going to skip, this allowed us to synthesize novel materials that hasn't been synthesized in single crystalline planar form before. Now, there is, I cannot say a library now, but a small library perhaps, of materials. And we are basically limited by the number of setups we have and number of people we have. If you name a material, I don't want to oversell it, but at least we can see what's happening and we can have an idea about the growth. Now, I'm going to give a glimpse of some of these materials. I'll just very quickly glance over them. But the focus, you can see, we don't have basically much data on these. That's why I'm not going to talk about them. But all of these materials exhibit very interesting phase transitions. At the moment, our focus is, materials that exhibit these phase transitions. One case is V2O3. Since I'm a VO2 guy, I always showed interest in VO2. But to be honest, our first goal was to synthesize VSE2, not V2O3, but you know, sometimes you get what you get. And you know, there are interesting questions that you can raise with very thin V2O3 crystals. And we basically studied the fundamental properties of these crystals. And perhaps an interesting point about V2O3 nanoplates that we synthesize is that you can exfoliate them. You know, it's not a van der Waals materials, but like ilmenite, where you can obtain monolayers, actually can sort of exfoliate. I don't want to call it exfoliation. This is not in the sense of, you know, you exfoliate van der Waals materials, but this is more like cleaving in the plane axis. But still, if you look at these steps, they're not optically visible. You can see actually, you know, it grows or it follows the unit cell of this material. And it's very important, actually, this ability to transfer these crystals is very important in this study, because now I can freely move around this phase diagram and I can study the full details of the phase diagram, unlike the previous studies. So I'm just going to go very quickly through these slides. But one other thing, you know, I had this dream of controlling the metal insulator transition using the using electric field. Now, actually, we are doing some very preliminary work to show, you know, these are preliminary results. We are working on it actively at the moment, but we have, it's showing hints of gate modulation. And thus, perhaps with better devices, not like these sketchy devices, better devices, we can control the metal insulator transition. But also, now we are working on suspending these nanoplates over these trenches where we can control the gap size and apply strain on these 2D material. Well, I don't want to call it 2D, but the thin crystal, and modulate the phase transition at various temperatures. Another one is manganese oxide nanoplates. You can find it in very different morphologies. Actually, you can buy kilograms of this material in the powder form, and it comes in very different morphologies. And this one is particularly interesting, at least for me, a guy who likes 2D materials. And but you cannot find single crystals of this thing until now. And basically, we can grow these crystals. They can be quite thin. Actually, we've recently found a 3 nanometer thick one, which is the record at the moment that we have. And if you could play this video as well, and perhaps speed up, because I realize that I have 20 minutes, not 30 minutes. So if you could speed up, like jump to a later point, maybe, so we can see. At the moment, we are torturing the device. We are applying 150 volts, maybe slightly forward. Yeah, you can see this phase boundary moving with the applied voltage. And basically, we studied this in detail, and we realized actually what we have is this layered structure that has potassium and water intercalated across the layers. And by applying these, this electric field, that was an exaggeration. Actually, you can induce this ionic motion at much lower temperatures. But this is a material that is intrinsically doped with potassium and perhaps water, and you can move them. And further, actually, there's the example. I mean, even with 10 volts, actually, you can separate them. And it gives this very nice hysteresis curves. And again, I'm going to quickly go through these, but this is a slow process, and it can be used as a memristive device. And we also showed that you can mimic the synaptic response in such KMNO2 device. And now we have, I'm going to skip this one, but we also now have sodium MnO2. And imagine making a junction of these two materials. Now you can make things like sodium-potassium junctions where you can transfer different ion types. and perhaps like lithium and calcium, so you can manipulate the charges in the system. Another interesting example that exhibits these phase transitions is Cu2Se. Again, you could find it in various morphologies, various forms, as thin films and so on, and people demonstrated that it exhibits this very peculiar phase transition at about 350, where it shows this colossal Seebeck effect. Then we approached this material and tried to synthesize, and after synthesizing, we realized that actually it has these cute corners that has different color contrast. And actually, again, these are videos, and you know, if, so it's hard to see, but you know, once we apply this 1.5 volt, actually you can, I'm not sure if it is clear, but yeah, now you can see the copper ions actually within the crystal are moving, and it results in a different type of phase transition. I'm going to skip the next video. And basically what happens is, you know, if you push it too hard, actually you can find copper ions that are leaking into the gold contacts, but the phase transition mechanism is actually different. This shows a 5 orders of magnitude change in the resistivity, and you can control it optically as well as electrically. So this is another material. So I don't have much time left, but okay, all right, great. So, but basically we can explain this by the motion of copper ions. This is a superionic conductor. What happens is basically copper ions can occupy different sites in the crystal. One of them is tetrahedral, the other is octahedral, so it can make jumps across these sites. This causes the, this is the reason we believe that for the phase transitions we observe. So to wrap up, basically, you know, this is the way to find, I guess, fascinating new physics, the correlation-induced phase transitions, and we are trying to synthesize novel materials to aid this task. Before finishing, I would like to thank my group and my collaborators and you for your attention. Thank you.
Now paper is open for discussion. Questions, please?
Thank you. It's really interesting, and then you look to the resistive switching.
Mm-hmm.
But you have a 2-point contact and this, and can you also expect this interface between gold and your crystal structure? This is my first question. Second question is about you have really nice the triangular crystal structure. Is there some kind of the angular dependence of this kind of? Did you try this one?
Okay, thank you.
Thank you.
So the first one, I don't think it's a resistive switching. It is something that I can really define as a phase transition, because it's not like we are applying too much current to induce the phase transition, and basically you're creating sites that are more suitable for copper ions to occupy the octahedral sites, which for some reason that we are not fully aware is, you know, 5 orders of magnitude more conductive. And once it's in that state, it is a metastable state. It remains in that state. So I'm not sure if it is really a resistive switching mechanism. Probably not. And for the shape of the crystals, I think it is dictated by various parameters that involves, you know, the temperature that you grow your crystals, and the substrate, and also the you know, symmetry of the material, symmetry of the unit cell. So, you know, sometimes we can get hexagonal shaped crystals because of the 6-volt symmetric nature, but that happens, let's say, higher temperature growths. Sometimes we get triangular crystals that happens at, you know, lower temperature growths. And for the, you know, this accumulation of different phases, it's an entirely different story. I mean, I couldn't possibly fit in a 20-minute talk, I should have talked entirely on Cu2SC so that I can explain it in detail. But again, there are two factors: the substrate effect, as well as the how rapidly you cool down the system. They affect how these phases are distributed within the crystal. I hope this explained your question.
Thank you. Thank you. I will have to proceed. I think this is a certificate of participation